Okay, our next presenter is Colby Evans. He's a fourth year PhD student in chemistry, and he knew he wanted to study science when he kept ruining TVs with magnets and couldn't figure out why. I bet your parents didn't want you to know why. They just said stop. Okay. The title of his presentation today is A Window into a More Energy Efficient Future.
I would like to start off by saying that buildings consume 40% of the energy we produce as a nation. And that's generally true for most developed countries. And that's more or less because we like to be comfortable. So there's a huge need for developing technologies that make buildings more efficient while helping us maintain our comfort. Smart windows are one device that really get at this problem. And they work essentially like a lithium battery you can see through. So if we have a window, we have a ceramic material called tungsten oxide on it, and we want our window to become tinted, we can flip a switch or press a button and we shove lithium into that tungsten. And if we want a normal window to be transparent again, we just drive the chemical reaction the other way, strip out that lithium, we have a normal window. The way that this can help increase building efficiency is because in this colored or tinted state, that tungsten oxide is really good at absorbing infrared radiation, that heat part from the sun. So it never gets in the building. We save a ton of money and energy on heating, cooling, and lighting. There's even a couple buildings on campus that have this technology. But if we take a closer look at what the surface could look like, it's kind of messy. What we're actually seeing here are nano-sized rods of that tungsten oxide. And they're all different lengths and widths, and they're connected in all different ways. And it's unclear how these individual differences impact the overall performance of a smart window. Do some particles work way better than others? Well, we've all been part of a team project, right? We know that some people work really hard, and some people contribute, and some people don't do anything at all. And our central hypothesis is that could be going on one of these smart window devices. So what I did is I developed a methodology that allows me to look at this tinting and becoming transparent for individual tungsten oxide nanorods. And what I found is that some are really great, and some don't work at all. So this is a group project on the surface of a window. And what I found is that the ones that work really well can tint much darker, turn colors 4 times faster, and last 20 times longer than a thick film of all of its buddies, just because of that dead weight. And I found that it even matters how they're interacting with each other. If they're laying next to each other or on top of each other has huge implications on the overall device performance. And through all this, I've been able to publish and file a provisional patent on an improved device architecture that can hopefully get us somewhere close to a more energy efficient and comfortable future.